All right, so I will start my talk. So first of all, this research has been supported by NSERC, CFI, and Ericsson Canada. And also, as it was mentioned, so I just moved to UBC this summer. That's why most of the research I'm presenting here was actually done at Concordia. All right, so this is the agenda of today. So I will give a brief introduction first, and then I will go through 3 of our recent works that focus on attack detection, attack investigation, and attack mitigation. All right, so I will give a brief introduction first. So we all know that during the COVID pandemic, we have seen a lot of people moving to cloud services. And as this Microsoft CEO said, so 2 years of digital transformation, adoption of cloud services has happened in the time of 2 months. And that effect actually stayed here after the COVID, after the pandemic. And that's because, of course, people have seen the great benefits of using cloud services. Like for the end users, they are much more convenient, cheaper, and easy to scale up and scale down. And for the providers, it can maximize their profit margin. They can optimize the use of the shared resource. So that's why the cloud service will stay here. So this is one of the kind of more traditional type of virtual environments where you have the cloud sitting on top of the physical servers, and then you basically use virtual machines, virtual networks. That's what people have been using in the past years. But then now, people are moving more and more towards the lighter weight container-based systems, such as Kubernetes cluster, right? So you don't need the entire complete VM virtual machines. You can just run your application inside a container, which is much lighter weight, much more agile. So not only that, we are also virtualizing the network. I'm sure have heard about software-defined networking. And then here today we're going to be talking about this NFV concept, Network Functions Virtualization, which essentially means that we are virtualizing those proprietary hardware network devices, like the DNS servers, and network switch, firewalls, etc. So we are converting them into software running on top of standard servers, and that is usually hosted on a cloud. Now, this NFV technique is very beneficial to both the tenants and the provider, and with the similar benefits I've already mentioned. But then, as it comes with benefits, it also comes with challenges. So the NFV tenants might be wondering, okay, since my network functions are sitting on top of the containers or virtual machines, I cannot see what is going on there. I cannot see what is going on in the underlying cloud. And if I cannot see what is going on, how could I know if someone is attacking me? Someone is dropping my packets and changing my packet forwarding, etc., etc. How could I even know? Right. So that's the first question we're going to answer today. Then for the cloud providers, they are facing different issues. First of all, how could you investigate an attack, the root cause of an attack, when you're talking about cloud scale data, when you're dealing with cloud scale data? And the second problem is, even if if you have found the root cause of the attack, if this vulnerability has not been patched by the vendor, it takes significant time, right, for a security patch to be released by the vendor. So if the patch is not yet available, what would you do? So those are the 3 questions we're going to answer in today's talk. So let's move on to the first one. This ChainPatrol was published as USENIX Security 2024. So let's look at the problem first. So we are talking about attacks on service function chains. So service function is basically nothing but that you are chaining up a few network functions, such as the firewall, IDS, DPI. So you are putting them into a chain. That's called a service function chain. So and those functions, of course, are running on top of some virtual machines, on top of some virtual switches. So you're expecting your packets to flow like that, right? It's going to be forwarded to your firewall virtual function, to be filtered there, coming back, and then go to the next IDS, DPI, right? That's what you're expecting the packets to flow. However, if an attacker somehow compromise one of the virtual switches, remember, it's not a physical device, it's a virtual switch, which means it's a software. It's very easy to compromise, right? So if the attacker can compromise this switch one, then he can certainly do a lot of things with your packets. He can make it bypassing the IDS and DPI. He can drop those packets. He can redirect the packets. He can inject his own packets. He can do some man in the middle, right? How those things might happen with the tenant having no clue, because again, the tenant cannot see what is going on, right? So let's look at in more details. So let's suppose this attacker compromised this switch and is injecting a malicious packet TR. So then again, as I said, as a tenant, I cannot see what is happening below in the underlying cloud layer. So the VNIF2, the virtual network function number 2, which is the receiver of this packet, has no idea. Oh, this PM has been injected by attacker. It's a malicious packet. It's not a legitimate packet. Okay, it has no idea about that. Then the cloud provider also cannot always solve this problem because he doesn't know the tenant's policy. Sometimes he may think this is normal behavior of the switch due to fault tolerance. It's replicating the packet, right? It doesn't. It's not keeping up with all the user policies. That's why he cannot always help. So then you see we have a gap. We have a research gap here. And then a well-known solution is this so-called crypto trader solution. We're talking about basically the integrity. And the standard solution for integrity in crypto is to use MAC, right? To use message authentication code. So what you do here is very simple. You add some numbers, okay? You add some index to each packet and each flow, and you see that, okay, so this packet here is the first packet of the first flow, okay? And to make sure attacker cannot modify those numbers, I add a MAC over the packet and all those numbers, okay? Then I attach this to the packet as a trigger, so that when attacker launches the same attack, he cannot compute the MAC, of course, and that's why he will be caught because his MAC doesn't match, or those numbers inside doesn't match, right? So that's the standard solution that works very well. However, the challenge is, remember, you are adding a crypto trader to every single packet. All right. Then if we are talking about, for instance, DNS traffic, this kind of where you have smaller packets, okay, then you are looking at up to 40% of additional communication overhead, okay, which basically cuts your throughput, network throughput by almost half. That's of course not acceptable, right? That's really not acceptable. So to solve this problem, our main idea is to basically virtualize those crypto traders, okay? So we don't really use the actual trader. We try to encode traders inside some side channel information. In particular, we're using the inter-packet delay. And I'm sure that many of you have heard about this. So basically, I delay the fourth packet, and I delay the first packet. Now what you're saying is, you see the distance of, in fact, the inter-packet delay are changing, right? The delay between P3, P4 is becoming larger, but the delay become P1, P2 is becoming smaller. And then I can use those smaller or larger than euro delays to encode the bits 0, 1 of my trailer, of my crypto trailer. Okay, so basically I can encode a crypto trailer without any single packet added, but using the interpacket delay like this. That's the main idea here. And this, and when attacker injects a packet, of course, we can detect it because now you have 2 zeros, because you can see there are 2 smaller than euro delays, right? So this is a very good solution. It allows us to have the best of both worlds. You can have provable security of crypto algorithm. You can also have the zero communication overhead that comes with SAT channel. But then the main challenge here is how you can encode a 256-bit MAC using this method. Because if you come back here, if you look at this, you can see that we can only encode 1 bit with every 2 packets. Okay, so to encode 256 bits of a MAC, that requires a lot of packets. Right? So that is a challenge. The solution is, of course, we have to group the packets. And in fact, we group the packets in 3 levels as the frames, block, and the superblock. I'm going to explain why we need that. Okay, so first of all, we are labeling each block just as we labeled the packet on the previous slide. We give a number to each block. And we also see this is the first block inside the first flow. That's why both are 1. And then we also have a MAC, but then that MAC is computed over the entire superblock, which might include 2 blocks or more than 2. Usually it's much more than 2, but for simplicity, I'm only showing 2 here. So we have computed the MAC over the entire superblock because, again, it's very long, has a lot of bits. It needs a lot of packets to encode. Right? So you can see we are using the first frame of the first block to encode the first number, the block number, the block ID. We're using the second frame to encode the flow ID. And then we're using the third to encode the first part of the MAC. Okay, so the MAC is divided into 2 halves since we have 2 blocks. But if you have, say, 100 blocks, then we'll divide the MAC into 100 segments. Okay, so that's all work. It is all good. And the second part is encoded in the second block, right? So that's all good, but then we found there is another major challenge. And this one is a bit tricky. So since the MAC is computed over the entire superblock, which means you cannot compute this MAC until you have received the very last packets of the superblock, right? But then at the same time, since you are encoding the first half of the MAC, first part of the MAC inside block 1, you cannot let block 1 packets go until you have computed MAC. Because, you know, how do you encode the MAC? Remember, you have to change the interpacket delay of those packets, right? That's why once you have let those packets go, once you have forwarded them, you cannot change their delay anymore, right? That's why you have to keep the block 1 here until you have received the entire superblock, computed the MAC, then you know how to change the interpacket delay of those packets here in the block 1. That, of course, is going to cause a lot of delay, right? That's going to cause a lot of delay that is totally not acceptable. So that seems we get stuck here. There's no solution, but of course, there is a solution. Our idea is this. It's very simple, but it's very effective, okay? We're not going to encode the virtual trailer of this superblock in the same superblock. Instead, we're going to encode it in the next superblock so that you'll have time to prepare for the next superblock. And to put that into detail, this is how it works. Okay, so can you ignore those details, but basically, when we have received the complete superblock 1, and we can compute the MAC, right? But we don't encode this MAC in the same superblock 1. We actually forward all the packets in superblock 1 as soon as they arrive. We don't need it. We don't need to keep them, right? because this MAC is actually going to be, this trigger is actually going to be encoded in the next superblock, which has not arrived yet. Okay? So we now have the entire trailer computed. We know what to do with each packet as they arrive. So when the first two packets of the next superblock arrives, we look at our block number here. We say, okay, the first bit is 0, which means I have to make the first two packets closer than normal, right? 0 means closer. Then another 0, again, closer, 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 and then the last bit is 1, which means, okay, now I'm going to make the last two bits here further away. Okay? So I know what to do with each pair of packets as soon as they arrive. That means I can make the changes, I can forward them right away with no delay. Okay? So that's the beauty of this idea. So how do we detect an attack using this once we have encoded the trailer? Very simple. You'll take two super blocks as a pair. Because remember, the trailer of the first superblock is encoded in the second superblock. That's why you need a pair. So you look at the first superblock, you see, oh, so this is the first block of the first flow. Let's decode the trailer from B3, because remember the trailer B1 is there, right? So and then we match, say, yeah, it says 1, 1. So yeah, that match, that's fine. Then we also encode, we also look at the MAC. We basically recompute the MAC over B1, and then we compare to the decoded MAC from B3. And if they match, we are fine. Okay, we know everything is fine, no attack. But even if anything mismatch, we know there is something wrong. And our solution can actually help you to not only detect the attack, we can also locate it. We can find exactly which packets have been attacked, what kind of attack, is it drop, is it modification, injection, etc. And those details can be found in the paper. So I'm not going to talk about that here. So of course, I'm sure many of you are thinking about this issue now, right? You are saying that you are using interpacket delay, but there could be network jitter. Those jitter could generate a natural change to those delays. So they are not really reliable, right? So don't worry, you have actually two solutions to address that issue. Again, due to the time limit, I'm not going to go through it in detail, but you can find it in the paper. So I'm going to go to the evaluation. So we have done experiments by deploying our solution on Amazon EC2. And we have tested its effectiveness, and we have shown that we can extract the watermark with 100% accuracy. It's easy to choose the right parameters to achieve that. And also the end-to-end latency due to this solution is around 2.1 milliseconds for the more traditional setting, and 0.68 millisecond for the 5G Kubernetes container setting. Okay, so which is really very, very negligible. We also tested the detection classification effectiveness. We found that the solution can achieve a perfect detection. And then its classification of the attack accuracy is around 70%. So there's still room for improvement. And this is mainly due to the fact that we have much less trailer. Remember, we can only embed 1 bit with every 2 packets, which means our trailer is much coarser grained than the physical trailer. So that's the main reason. But as I said, there's still room for improvements. Okay. So we compare to the physical trailer solution, we show that you could potentially free up 45% of the communication of the original traffic. So basically, we can save up to half of the traffic. So that's a significant benefit of the solution. So as a summary of this work, so our solution achieved a kind of better balance, better trade-off among those 3 factors. Okay? While the traditional physical trailer is more towards security latency, but it suffers from a high communication error. Right? So I will move on to the next work. Yeah, so the next work focus on attack investigation. It was published this year in S&P. So as I mentioned, when the analysts are dealing with cloud scale network and attacks, they are dealing with also a huge amount of data from all the different logs. So that is extremely difficult to analyze. So one well-known way to help the analyst is to convert those logs data into a so-called provenance graph. Right? So basically, the graph allows the analyst to trace back to the root cause from the given alert, to trace back to the potential root cause by following the causal relationship between events. Right? And that's a well-known technique, but it's also well-known that those graphs tend to get very large. And again, if we're dealing with cloud scale network, this graph could become gigantic. So it can be very overwhelming for any human analyst to analyze, to investigate, right? So that's the main challenge here. And then, of course, there exists a lot of pruning solutions to reduce the size of the graph. But each of them has their own limitation. For instance, you can search backward from the given alert or point of interest, okay? And you can prune out the other nodes that are not inside the search. But then this solution actually could lead to a dependency explosion. As you can see, you can continue going with no end to it, right? So it doesn't solve the problem completely. You can also use some anomaly-based solution to assign risk scores to each event, and then you can focus on the high-risk scores, right? But then again, as any anomaly-based solution, you need complete training data. Otherwise, you would have a lot of false positives. Graph theory features, you can look at node degrees. This node is suspicious. It has a lot of incoming, outgoing edges, right? But that is ignoring the semantics of the node. You're not saying what is the node, right? You're just looking at the graph theory features. You can also limit the search to a certain length of the path. Okay, so I'm going to only look at nodes that are close enough to the alert. But then, of course, you may have false negatives because some event might be further away, but still relevant to this alert. And then all of those solutions show very high, they could become very expensive. But instead of addressing each of those limitations, which we actually didn't do, okay, what we did is that we look at them as a whole. We ask ourselves, what is the common limitation here? What is the common to what they're doing here, which is not good enough? Now we found, yeah, there is something. They all regard this point of interest alert as an abstract graph node, okay? As the beginning of the search and so on. Okay? They don't explore further this alert itself. And we realize that is really missed opportunity because this is an alert. An alert is typically associated with a lot of useful external information, such as the IDS rules used to detect the alert, right? The CVE information related to this alert, and so on and so forth. Why don't we tap into those external information? So that's the whole idea behind our work. Okay? So what we do is we extract information from external source. We kind of allow them to come into the provenance graph by mapping them to some of the nodes in the graph to identify what we call the waypoints, which are basically additional point of interest. And then we correlate those waypoints and point of interest, okay, into a kind of shape that include all the relevant nodes to this alert. So that's the whole idea. And to realize this idea, of course, it takes a lot of work, a lot of details I'm not going to be able to cover, but you can find them in the paper. So basically, we have to build a system lexicon for, we are focusing on Linux kernel attacks. So we build a Linux lexicon to know which information we need to extract from the external source. We build a knowledge base. We use those information to generate queries, so we can map them onto the provenance graph. Okay, and then I know as a point of interest, waypoints, and so on, different type of nodes. And then once we have that, we also do some pruning of the waypoints to make sure we only keep those that are truly relevant to this alert. And then after that is done, we go to the last and the most important step, which is correlation. We correlate those waypoints and point of interest. And we have explored different methods from the naive, kind of naive methods, only look at the shortest path, to the most sophisticated methods like we also explore the vicinity, the nearby nodes to the nodes on the path. And also, we also add more semantics to this method by looking at the dependency between process. We use the parent-children process to add further to this method. And eventually, we also have the conditional expansion, which means we realize that we have to stop the expansion at certain points because of potential dependency explosion. So in the end, we have a complete methodology to find the correlation that is most effective. So we tested our solution as a standalone solution on 20 kernel CVEs. And our results show that we achieved 100% true positive for 19 out of 20. Only one of them, we have about 96%. And then the false positive is below 0.6 for 16 out of 20. And false positive here means basically we are not pruning some nodes, which we should prune, right? So you see, it's not that big deal. The humanities can still filter them out later on. But so we also evaluated our tool as a preprocessor for some existing pruning solutions. So we have identified some common pruning solutions from related works that may apply our solution as a preprocessor. Then our results show that it could help those solutions to reduce the number of false positives from thousands. In fact, we have up to 150 or 160,000 false positives from some of those methods, but we can reduce them to less than 50 false positives in all cases. And 50 false positives is something a human analyst can handle, right? So that's the main benefit of this. We also performed the real-world user study. We invited participants from both industry and academia to evaluate the work. And we have overwhelming results saying this tool is indeed very useful. So as a summary, so as this meta review comment is saying here, so I guess the lesson here is that when you have worked on some topic for too long, it might benefit you to look outside the window to find new lights, to find new and that's exactly what we did in this work. Right, so I'm going to move to the last work, which focused on attack mitigation, in particular to temporarily patch the vulnerabilities that don't have any official patch. So this was published in NDSS 2024. So the existing approach to security patching is this: we have to wait for the software vendor, like Microsoft, or Google, or whatever vendor, to release the official patch. And that generally could take a long time. And I have statistics showing that every delay to an official patch is about 100 days. Okay, so since the vulnerability is discovered, you have to wait about 100 days for the patch to be released. And because this development of patch is a very complex process, it involves many different steps. Okay? But then as a result, you see that this famous example, right? So the many Canadian government websites were shut down because of this log4shell vulnerability and because we are waiting for the patch. Okay? So that's something not very acceptable. Now, our idea, our approach in this paper is that we are proposing a different way of doing security patching, which could potentially reduce the delay to a few days. And this is the idea. So instead of relying on the vendor, we ask all the affected users to come together through crowdsourcing, okay, to find out, not the patch. They are not going to find the patch, right? We ask them to find out what the patch would look like, in terms of blocking system calls. Which system calls you should block in order to prevent any exploitation of this vulnerability? That's a question we want the affected users to answer through attack investigation, using the provenance graph that you have just seen. And so once we find that, okay, so that patch should look like a circle, all right? Let's make it that simple. Then we give that information to our tool Phoenix, and Phoenix is going to start blocking syscalls that are involved in this exploit. So any future exploit of the same vulnerability will be essentially blocked. Okay, so that works as a temporary patch while you are waiting for the official vendor patch. So that's the whole idea. So the attacker will be blocked. So that's sort of like one way to patch them all, right? So I know that's a big ambition, but at least we're heading there. So how we can do that? So let's learn from the visa. So I'm sure if you have any international or any attendance from other provinces, I'm sure you have just gone through this kind of chaos, right? So we know what happens at the airport. If you are Canadian or if you are permanent resident, you will be let go very quickly. You will be asked 1 or 2 questions, right? And then they will let you go. It's a very easy, very fast process for you. But then for all the other guests, right? For the other guests from other countries, especially from some blacklist countries, right? Then what might happen is you might be let into a small room and then sitting there for 2 or 3 hours, right? To have a friendly conversation with an officer there. Right? So I'm sure that how either experienced it or heard about it. Well, this selective processing of different cases is actually the idea we can learn from the risk officers, which will apply to our problem. So here's the key idea of the work. First of all, so the Seccomp is a standard Linux kernel feature used to block syscalls. Okay, so and it works like a risk officer, asking questions. And then if you apply Seccomp to block syscalls, most people do it in this way. They block the syscalls that are not needed, not used by the container. It makes sense, right? If the container is not using those syscalls, why do we need to allow them? We should block it. This is fine. This reduces the attack surface, but it's not secure because if the attacker is smart enough, he's using the same syscalls as the container is using, then you will let it go. Seccomp will let it go. So you're still subject to the attack. Right? Now, if you decide to do the opposite, if you decide to block those syscalls regardless, then what happens is, since they are also used by the container, so that the container will no longer function normally, right? Because you are blocking too much. You are blocking the syscall needed by the container, right? So this blocking is not accurate because you are not looking at the arguments, because it's not just syscalls that matter. Their arguments also do. Well, to address that, you can use another tool, a kind of user space tool, ptrace, which you can use to actually inspect, analyze the argument of each syscall. to know which one match, which one does not, which one to block, which one not to block, right? So that sort of work like the more thorough investigation by the officer, you know, stay there for 2-3 hours, right? But then we know that the solution is accurate, but it is not efficient. It can take a long time if you do it for every single Syscall. That's why what we do in our solution is to combine those two. Like I said, you know, selective processing, different kind of processing for different cases. So if the Syscall that we just received, if it doesn't match what we are looking for, okay? If it's something else, something that is not it's a different type of Syscall we're looking, we just let it go. It's like if you're a Canadian, if you're a permanent resident, we know you don't have much risk, so we just let you go very, very fast. But then if it matches what we are looking for, that's the time we are going to lead you into a small room. We sit you there for 2-3 hours asking all sorts of questions, right? So which means we are using ptrace to have a thorough investigation of the Syscall argument and so on to know if it is the right Syscall we are looking for. If it is, of course, if it is not, we still let it go. If it is, we block it to ensure security. So in the end, we have the efficiency, we have the accuracy, we have the security. And moreover, what we do is, since we have found the first Syscall we're looking for in the sequence, we know this attack comes with a PEP Syscall followed by an open Syscall. Okay, that's the signature of the attack. All right, now we have found the first one. Now we should be looking for the next one, the open call, right? So that's why we go back to our Seccomp filter here to tell it to update what he's looking for to be the new Syscall open. So that way we can dynamically update the Seccomp filter to inspect a sequence of Syscall, you know, not just each Syscall by itself, but a sequence of it. Okay, so that's a key idea of this solution. And in the end, we can have the container protected, function normally without much delay. We have the best of all three. So to achieve that, we actually leverage the previous provenance graph-based attack investigation to identify the malicious sequence we want to block. Once we have that, we use it to build a finite state machine so that we can monitor all the incoming Syscalls to do the matching. And whenever we find a match, we just block it. Otherwise, we let the Syscall go. Okay, so that's the whole idea behind this solution. And also, as I said, we recommend to use crowdsourcing to come up with the sequence in a much shorter time. And then you can give that sequence to Phoenix, which will apply it to every affected user. So all they need to do is to install Phoenix. They don't need any other software, just one piece of software with different sequence. You can kind of block different vulnerabilities. So we have evaluated our solution on 20 real-world CVEs, and the results show that we can block all of them. And in fact, some existing solutions can only block some of them. So we have better coverage. We also compare to some existing stateful solutions for blocking vulnerabilities through blacklisting. And what we found is that those tools, those existing solutions, they can be easily fooled with some slight variation of the, you just change some sequence and of instructions, and those tools will be evaded. But Phoenix can still block all those variations very effectively without any false positives. We also look at the overhead because we're talking about Syscalls. So, you know, the overhead is can be very sensitive there. So our results show that Phoenix incurs very negligible overhead compared to Seccomp. It's almost the same as Seccomp. And even though we are actually using very expensive tools like ptrace to inspect the Syscall arguments. It also incurs quite low, quite negligible results. So as a summary, it's sort of like a Swiss knife for security patch. Basically, you can use the same tool to patch different kind of vulnerabilities. And all it takes is some attack investigation effort. Among all the affected users, they come together to find which sequence of Syscall to block. So that's all it takes. All right, so I think that's actually all I have. So